Hi boys and girls, today we begin Unit 6, the topic Transcendental Functions. Our first lecture, 6.1, is entitled The Natural Logarithmic Function Differentiation. We're going to begin with a review of the general power rule for integration. Here the integrand is x squared. If we add 1 to that exponent, we'll get x cubed. And of course we need to divide by that new exponent, giving us 1/3 x cubed plus c. Here we have x to the 1. Adding 1 to that exponent gives us x squared. And dividing by that new exponent, 1/2 x squared plus c. X to the -1, when we add 1 to -1, we get 0, x to the 0. And how do we divide by 0? This is a bit of an anomaly. Let's see about x to the -2. When I add 1 to this exponent, I get -1, and I am able to divide by -1, giving me -x to the -1, which can be written as -1 over x plus c. And then x to the -3, if I add 1 to -3, I get -2. And of course, dividing by that new exponent gives me -1/2 x to the -2, which can be written as -1 over 2x squared plus c. But what is happening here? This has to be able to be integrated, but how do we use the power rule to integrate when adding 1 to -1 gives us a 0? Well, this is going to provide the foundation for what we're going to discuss today, which is the natural logarithmic function. The natural logarithmic function is defined to be that integral. The integral of 1 over t dt is the natural log of x. Thus, if y equals the natural log of x, then y prime is equal to 1 over x. Here is a graph of the natural logarithmic function. Here are a few characteristics that we should take note of. The domain of the natural logarithmic function is 0 to infinity and not including 0. Therefore, what can you insert in for x? Positive numbers, not 0 and not negative numbers. And so that's why 0 serves as a vertical asymptote for this function. The range of the natural logarithmic function is -infinity to +infinity, so all of the y values are ultimately going to be used. This function is continuous, so on its domain there are no breaks, no asymptotes. It's continuous on its entire domain. It is also increasing on its entire domain and concave down on its entire domain. So note what that means. The first derivative of the natural logarithmic function is always positive, and the second derivative of the natural logarithmic function is always negative. Now that we're discussing logarithms again, let's review some of the properties that we've seen previously. If a and b are positive numbers and n is rational, then the following properties are true. The natural log of 1 is 0, so that's just a factoid that you need to remember. This is called the product property. If your argument of the logarithmic function is a product, ab, then that can be separated into a sum, natural log of a plus natural log of b. And here we have the exponent property for logarithms. If the argument is a quantity raised to a power, that exponent can become the coefficient of the logarithmic function. So natural log of a to the n can be rewritten as n times natural log of a. And then finally we have the quotient property for logarithms. If the argument of your logarithm is a quotient, a over b, that can be rewritten as a difference, natural log of a minus natural log of b. So it is helpful sometimes to take the argument of the logarithm and use these properties to simplify the expression, which is what we're going to practice doing here. First of all, let's rewrite this as natural log of 3x plus 2 to the 1/2 power. This means we can use the exponent property and bring this exponent around to become the coefficient of this expression, 1/2 times natural log of 3x plus 2. Now let's look at number 2. Since this is a quotient, we can use the quotient rule and separate it into a difference of two logarithms, natural log of 6x minus natural log of 5. But then notice this argument is a product, which means I can use the product rule and separate that into a sum of two logarithms, natural log of 6 plus natural log of x minus natural log of 5. And finally, for number 3, first of all, we're going to use the quotient rule to separate the numerator from the denominator, and that will give us natural log of x squared plus 3, quantity squared, minus natural log of x, and I'll write the radical expression as x squared plus 1 to the 1/3 power. Now, as I continue to simplify, I can see that in this first expression, I'll be able to use the exponent rule and bring that around to become a coefficient. So this will be 2 natural log of x squared plus 3, and then minus, I'm going to do simplification here using the product property, separating this product into two logarithmic expressions. But the negative that I have here will need to be distributed to both of those expressions. So this will be natural log of x, and then plus natural log of x squared plus 1 to the 1/3 power. Now continuing to simplify, on the next line, I'll have 2 natural log of x squared plus 3. I'm going to distribute the negative to this expression and this one, and for the final simplification, I'm going to bring this exponent around to become the coefficient of this logarithmic expression. So this will be minus natural log of x, and then minus 1/3 natural log of x squared plus 1. Now notice the original expression and how complicated the argument was, and then the simplified expression using the properties of logarithms. This will be very helpful when we begin to differentiate logarithmic functions. As you know, logarithms always come with a base, and since we've been discussing the natural logarithmic function, you may have been wondering, what is the base of the natural logarithmic function? It turns out that the number e is the base for the natural logarithmic function. It is an irrational number with the following decimal approximation. And here is that approximation. It's a number like pi or any other irrational number. Since natural log of e is equivalent to log base e of e, natural log of e is 1. Another little factoid that you're probably going to want to commit to memory. Now let's evaluate a few natural logarithmic expressions. And before we do, let me point out that this is all calculator work. There are 2 logarithm buttons on your calculator. LOG is called the common logarithm, which is base 10, and LN is called the natural logarithm, which is base E. So we're simply going to press the appropriate buttons on our calculator, and the decimal approximation will then emerge. For natural log of 2, we should get this decimal approximation, 0.693. Natural log of 32 should yield 3.466, and natural log of 0.1 will produce this approximation, negative 2.303. So this was just practice in using the natural logarithm button on our calculators. Now for some calculus. The derivative of the natural logarithmic function. If u is a differentiable function of x, then the derivative of the natural log of x is 1 over x, and we should not find this surprising since we defined the natural logarithmic function as the integral of 1 over x. So the derivative of natural log of x should be 1 over x. And then if u is a function of x, the natural log of u will be 1 over u times the derivative of u, du dx. Or this could be written as u prime over u. Since the argument of the natural logarithmic function is always positive, these are the disclaimers that we have as far as keeping the argument positive. Now, let's practice taking some of these derivatives. I am always going to exhort you to use the logarithm properties to simplify the argument of the logarithm first before taking the derivative. So we're going to first of all just rewrite this. We're going to take the derivative of this function, natural log of 2 plus natural log of x. Since that was a product, we could turn it into a sum. Well, the derivative of natural log of 2, since that is actually a constant, is 0. And of course, the derivative of the natural log of x is 1 over x. So that is your derivative. Now we can't use any properties to simplify this argument, so we're going to take the derivative of the natural log of x squared plus 1. It's going to be 1 over the argument x squared plus 1, and then you multiply by the derivative of that argument, which is 2x. So this becomes 2x over x squared plus 1. For the third example, we're going to have to use the product rule. The first times the derivative of the second will produce x times 1 over x, and then plus the second function, natural log of x, times the derivative of the first, which is 1. Well, x times 1 over x simplifies to 1, so this derivative turns out to be 1 plus the natural log of x. And for our fourth example, we will have to use the power rule first. Notice there's an exponent here, so we'll have 3 times natural log of x, quantity squared. Chain rule is going to apply now, where we're going to take the derivative of what's inside times 1 over x. So this can be rewritten as 3 times natural log of x, quantity squared, all over x. In this example, we're being asked to differentiate this logarithmic function. Notice how complicated this argument is. If I were going to take the derivative as it is, I would need to say 1 over this whole thing times the derivative of this argument, which would involve the quotient rule, the chain rule, a little bit of product rule, far more crazy differentiation than I really want to perform right now. Or I could use logarithmic properties to aid me in differentiation. Rewriting this logarithmic expression using these properties will give me a much simpler function to differentiate. So that's what I'm going to do. First of all, I'm going to separate the numerator from the denominator by using the quotient property. This will become natural log of x times x squared plus 1, quantity squared, minus natural log of, rewriting the radical expression with a rational exponent, 2x cubed minus 1 to the 1/2 power. Now I'll use the product property to separate this into two different logarithmic expressions, natural log of x plus natural log of x squared plus 1, quantity squared, and I might as well use the exponent property to bring this 1/2 around to become the coefficient of that logarithmic expression, minus 1/2 natural log of 2x cubed minus 1. Now one final bit of simplification using the power property again, or the exponent property again, allows me to bring it around to become the coefficient of that term, plus 2 times natural log of x squared plus 1, minus 1/2 natural log of 2x cubed minus 1. This is the original function, rewritten using logarithmic properties. I haven't done any calculus yet, but notice it's going to be much simpler to take the derivative of this function than the original form. So let's do that. F prime of x is going to be 1 over x, then plus 2 times 1 over x squared plus 1 times the derivative of x squared plus 1. Don't forget to multiply by the derivative of that quantity. Then minus 1/2 times 1 over 2x cubed minus 1 times the derivative of 2x cubed minus 1, which is 6x. And let's simplify the derivative a little bit. F prime of x then will be 1 over x, and then 2 times 2x yields 4x in the numerator, over x squared plus 1, minus 1/2 times 6x over 2x cubed minus 1. I should have gone ahead and simplified that there, so I'll write one more step. F of x is equal to 1 over x plus 4x over x squared plus 1, and then negative 1/2 times 6x gives minus 3x over 2x cubed minus 1, and that's your derivative. In this example, we're going to see that on occasion, it is convenient to use logarithms as aids in differentiating non-logarithmic functions. This procedure is called logarithmic differentiation. Notice we're being asked to find the derivative of this function. It is not a logarithmic function, but it is a bit complicated. This would require the quotient rule and some chain rule action. So let's try something new. Let's turn this into a logarithmic function by adding natural log to both sides of the function. Natural log of y is equal to natural log of x minus 2 quantities squared over x squared plus 1 to the 1/2 power. Notice that turning this into a logarithmic function allows me to use logarithmic properties to simplify this argument. So let's do a little bit of that simplification. Natural log of y then is going to be natural log of x minus 2 quantities squared minus natural log of x squared plus 1 to the 1/2 power. Using the exponent rule, I can bring these exponents around to become coefficients. And I end up with natural log of y is equal to 2 natural log of x minus 2 minus 1/2 natural log of x squared plus 1. Now let's take the derivative. This is going to be 1 over y times the derivative of y. And since we're ultimately going to be solving for y prime, let's write this as y prime over y. This is 1 over y times y prime is equal to, this will be 2 times 1 over x minus 2 minus 1/2 times 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. This becomes y prime over y is equal to 2 over x minus 2 minus, and since 1/2 times 2 is 1, this will end up just being minus x over x squared plus 1. Okay, now we do need to solve for y prime here. So we are going to have to consolidate these two separate rational expressions, consolidate this into one rational expression, multiply both sides by y, which is the original function, in order to ultimately solve for y prime. We'll do that on the next slide. Okay, here's where we were in this process. We're going to consolidate these two rational expressions into one, so we need a common denominator. And the common denominator of x minus 2 and x squared plus 1 is, of course, x minus 2 times x squared plus 1. So this expression is going to need to be multiplied by x squared plus 1 over x squared plus 1. And this expression is going to need to be multiplied by x minus 2 over x minus 2. Resulting in 2 times x squared plus 1 minus x times x minus 2 all over x minus 2 times x squared plus 1. When I distribute and combine like terms, I'm going to end up with 2x squared plus 2 minus x squared plus 2x, which I'll just go to the next line and continue simplifying. Y prime over y over this denominator. We get that right. And then this is now going to be 2x squared minus x squared is x squared plus 2x plus 2 over x minus 2 times x squared plus 1. Now it's time to multiply both sides of this equation by y in order to solve for y prime. But we need to multiply by y in the form of the original function, which means we're going to multiply x squared plus 2x plus 2 over x minus 2 times x squared plus 1 times x minus 2 quantities squared over x squared plus 1 to the 1/2 power. This is y, the original function. And so our final answer then will be y prime is equal to x squared plus 2x plus 2 times x minus 2 quantity squared over, and since we have x minus 2 here, x squared plus 1 to the 1 power times x squared plus 1 to the 1/2 power becomes x squared plus 1 to the 3/2 power. One final simplification, this x minus 2 term can cancel with one of the ones in the numerator, giving me x squared plus 2x plus 2 times x minus 2 over x squared plus 1 to the 3/2 power. So this is a way to use logarithmic properties, even though the original function was not a logarithmic function, in order to simplify the function and take the derivative. That's it for today's lecture. I leave you with this quote from mathematician Hilda Phoebe Hudson. To all of us who hold the Christian belief that God is truth, anything that is true is a fact about God, and mathematics is a branch of theology. This diagram is so interesting because someone has drawn what looks like a tree with many of the branches of mathematics. Here is integration, for example, and definite integrals, area under a curve, which is something we have discussed recently. Here's the differentiation branch. You have chain rule, product rule, quotient rule, increasing functions, decreasing functions, derivatives of many of the transcendental functions. Then we move to the functions branch where you have categories of functions: quadratic, cubic, exponential, logarithmic, which was the topic of our discussion today. You also have the trigonometry branch, the vectors branch, the algebra branch, coordinate geometry, series, equations. I wouldn't blame you at all if you were tempted to gaze upon this beauty for hours, but I would advise you not to do so because, after all, you do have a calculus assignment. God bless you, boys and girls.